Welcome to another video on the quantum chemistry series on the IGetChem channel, where we help you learn chemistry the easy way by showing you how to solve problems. Today's problem is on the harmonic oscillator. The harmonic oscillator in chemistry is a model for molecular vibrations, so this is a key problem that we need to understand for quantum mechanics. So let me read through the problem first, and we will get right to the solution. A, describe the nature of the eigenfunctions of the one-dimensional harmonic oscillator. B, show that the Hermite polynomials obey the following recurrence relations, and they're written here. I'll let you read them yourself. The Hermite polynomials are part of the eigenfunctions of the harmonic oscillator, and they have these some of these very interesting recurrence relations. And part C show how these recurrence relations are related to the effects of applying the position operator x on the eigenfunctions of the harmonic oscillator. Okay, so let's get to the solution. So as we have said, the harmonic oscillator is typically used to represent the vibration of a bond in a molecule. So if you simply think about having two atoms which are bonded together like this by some kind of a bond which we can think of as a spring, so this is atom A and that is atom B, then the harmonic oscillator problem describes the vibration of that bond when it is once it is being stretched and then released. Oftentimes you can represent, even though there are two atoms, you can represent the problem as a function of the stretch distance between A and B. So you really have, even though there are two particles, you really have only one internal coordinate between them, which is essentially the distance between them, and that we call x. So as a result of that, you can actually calculate what is called the reduced mass between A and B. Instead of just using the mass of A and B, the reduced mass has this formula: 1 over ma plus 1 over mb is equal to 1 over the reduced mass. So for this effective one-dimensional system, with x being the separation between A and B, the mass that you would use would be mu instead of ma or mb. So it would look like essentially a one-dimensional vibrational problem. The form of the potential for the one-dimensional harmonic oscillator is a parabola. So the potential as a function of x would look something like that. The coefficients in front of that x can be written in two different ways. Sometimes you will see it written as 1/2 k x squared, where this k is called the force constant, and you sometimes will also see it written another way, where this is written as 1/2 times m omega squared x squared, and m is the mass. As we have said, usually we just use the reduced mass mu. It's easier for me to write m instead of mu, so I'm just going to keep m, but you have to understand that m, when you use it on the diatomic molecule, would correspond to really the reduced mass. So the omega in this case is essentially the natural frequency of the oscillation. That is classically the harmonic oscillator. When you stretch it and release it, will then vibrate with a characteristic frequency, that is omega. So you often see it written either 1 in either one of these two ways. On the other hand, we also know that the Hamiltonian is a sum of the kinetic energy operator T and the potential energy operator V, and V, as we have said, is equal to 1/2 m omega squared x squared, but T, you know, is minus h bar squared over 2m d squared dx squared, and V is 1/2 m omega squared x squared. So the eigenfunction, eigenvalue problem that we have to solve is the Schrodinger equation. And the Schrodinger equation basically asks us to find the solution of this eigenfunction, eigenvalue problem, where h is defined by this operator right there. Okay, so we are going to take a look at some of the wave functions that you will find by solving the Schrodinger equation for the harmonic oscillator, and along the way we will talk about some of the aspects of these solutions. I think a lot of times we get sort of bogged down by the mathematics, and so it's important when you go through these quantum mechanics problems that you not really get confused by the mathematics, but try to focus on what the mathematics is actually telling you about the quantum mechanics. So when you look at this problem is a little complex, because there are actually two parameters in the problem. So basically you have this coefficient and you have the second coefficient. I'm going to call the first coefficient A and the second coefficient B. So if you just rewrite the Hamiltonian using A and B, you see that the Hamiltonian is just A, or minus A, d squared dx squared plus b x squared. Okay, so that makes it a little bit more obvious, because sometimes there are just a bunch of parameters and you need to look at the structure of the problem more easily without focusing on those parameters. But why are there two parameters? Well, you can see that there are two because the first parameter A depends on the mass. So the mass is right there. Maybe I should choose a different color so that you can see better. So the first parameter A has a mass in it, and so the mass is right there. Whereas the second parameter has a mass, which is essentially determined by A, but then it has another parameter, which is omega. Now, of course, the mass and omega are two independent parameters, so depending on the system that you have, you will have a different combination of m and omega. So that's why you have two coefficients, A and B, because they essentially reflect the fact that you should have two independent parameters in the system. And so the equation that we have to solve is minus a d squared dx squared plus bx squared equals to some eigenvalue multiplied by psi. Well, actually, this is just h, so let me just write that down here. So this operated on psi of x should come out to be some constant times psi of x. So this is the equation that we need to solve. So let me just circle that. Now, as we solve these equations, it's important to focus on what you're trying to get at the end. And because of the fact that there are these different parameters in the equation, sometimes it's a little bit more work to try to sort of figure out where these parameters go. So the thing is, would it not be nice if this equation, instead of having A and B in front of the two terms on the left, instead of having A and B, it would have been really a lot nicer if this was just d squared dx squared with a minus sign and a coefficient of 1 plus x squared with the second coefficient being equal to 1. So that would have been a lot easier to solve. I mean, that equation would have been a lot nicer, right? That way you don't have to worry about these two coefficients. So the question is there actually a way to turn our mathematical equation in such a way that we can forget about those two coefficients and they will come out in some other way? So if you have watched our video for the particle in the box, which is a problem describing a one-dimensional system trapped inside a box of length L, so this is L, and the coordinate of the system within the box is described by x. And in that video, I'll make a link to that at the end of this video, you discover that one way to try to help us more efficiently handle the mathematics is to define this variable y. So we define a transformation of coordinate from x to y such that y is x divided by L. So now, because L is the length, x is the actual position within this box, then x divided by L would be anywhere between 0 and 1. And so the transformation of x to y makes the problem a little easier to deal with. Now, in this case, what we might actually do is to try to find the same kind of transformation by defining a new variable y equals to x divided by some length L. But in this case, it's not so clear what is the correct length to choose. The reason is because we said that it would have been nice if we choose a length such that it would come out to be, to give me coefficients of both terms being equal to 1. So you can ask, well, if I do that, replacing x by y times L, I will transform the Schrodinger equation on the left to minus a divided by L squared, d squared dy squared. And the second term would have come out to be bl squared times y squared. And then that now operated on psi of y should give me back e times psi of y. So the question is there a particular value of L that you can choose to make both of those coefficients come out to be 1? So obviously what you could do is to, let's say, make that equal to 1. And for that to be equal to 1, you set bl squared equal to 1. And so that will define what L is supposed to be, because then you would see that L is, if you simply choose L squared equals to 1 over b, this term would have become 1. So that solves one problem, but there's really no way that you can use that particular choice of L to scale away the first one too. The reason is very simple, because we said that a and b are two essentially independent parameters. If you choose L so that the second one becomes 1, certainly you're not so lucky that the first one would also become 1. So that really doesn't work. The idea that you can maybe scale away both of these coefficients is not going to work. So whichever that idea was, it's certainly not going to work out. But while that is impossible, there's another thing which actually is possible, which is to see if we can actually choose a particular value of L in such a way that we can make both of these, the first and the second one, instead of being a 1, make both of these equal to the same number. So instead of being equal to 1, let's make them equal to the same number. So I'm just going to represent that by basically some factor. Let's say we choose a particular L with these two coefficients are both equal to the same value, then the Schrodinger equation would now be equal to minus this value, d squared dy squared, plus the same value times y squared, and now this operated on psi will give me back psi. So even though we aren't able to make both of them come out to be 1, we can actually make both of them equal to each other. And you can see why that is, because I only have to set the first one equal to the second one to figure out what the correct choice of L should be, because I want to make A divided by L squared equals to B times L squared. And you can easily see that to make that work out, I can simply choose an L such that the fourth power of L is just equal to A over B. And if I've made that choice, then both of these coefficients will come out to be exactly the same number. And so as a result of that, I can just divide that through by divide the equation through on both sides by that number. And so you see this is just E divided by whichever that number is multiplied by psi. So that would have left me with the goal that I had set out for myself to do, which is to simplify the left side of this equation so that both coefficients are gone. And now all of that is basically put onto the right side of the equation. So let's figure out what this coefficient is. So we said that the proper choice of L is to make A over B equals to L to the fourth power. So let's look at the equation again. So this is A, this is B. So what we can do is to put those back into the equation. So A is h bar squared over 2m, and then B is 1/2 m omega squared, and that is supposed to give me L to the fourth power. So when you look at that, 2 cancels, you see that this is simply h bar divided by m omega to the second power. So L to the fourth is equal to that, and so L is equal to the square root of h bar divided by m omega. Okay, so if we had made that choice, then we can simply use that to calculate this coefficient. So this is both equal to A over L squared, right there, as well as B times L squared. You can use either one because we have chosen L to make both of those equal to each other. So either one would have given you the same answer. And so when you do that, you see that this is equal to, let's choose BL squared because that's a little easier to do. So you see L squared is just one factor of this instead of the square of this. So let me write that down. So L squared is h bar over m omega. And now B, as we have said, is 1/2 m omega squared. So if you look at that, then you can see that BL squared will turn out to be 1/2. 1 power of m cancels with 1 power of m below. And 2 powers of omega, one of them will cancel with 1 omega below. So what you're left with is 1/2 h bar omega. So let me maybe use the same color. Or I can write it as h bar omega over 2. And that is what this is. So what we can then do is to finally rewrite this Schrodinger equation into this somewhat simpler form, or very much simpler form, by writing it like that. So this is psi of y. And now this is whichever E is, but divided by h bar omega over 2. So E divided by h bar omega over 2. So you see, in this case, whichever the eigenenergy will come out to be is essentially measured in units of h bar over 2. So this is important, and that will be the starting point of the Schrodinger equation, which we can solve, and that makes it a lot simpler. Okay, we're not going to go over the entire solution because it's certainly in your book. The reason why I want to go over this is to show you that there is actually a way to simplify the mathematics so that you are not sort of bogged down by looking at all of these coefficients. So as we have shown you in this problem and also in the problem on the one-dimensional particle in a box, there are effective ways of scaling the distance so that you can actually make this work. And you will see in some of the other problems that we will do videos on that the same scaling would actually work for those other problems too. So now that we know this is the equation we have to solve, let's focus on that and see if we can figure out what the solutions are. Before I do that, let me just write it slightly differently. I am going to rewrite this so that this is just equal to some epsilon, and epsilon is defined as E divided by h bar omega over 2. And as we have said, this is the basic unit of energy. So the Schrodinger equation that I need to solve can be easily written as minus d squared dy squared. And let me just write the psi in there, plus y square psi, and these are functions of y, is just equal to epsilon times psi. So again, this is the key equation that we want to solve. So let's see if we can sort of figure out what the eigenfunctions are for that equation. Now, if you look at this equation, then you can clearly see that one functional form that can solve this Schrodinger equation is this one. So I'll just write that as psi of y equals to e to the minus y squared over 2. These functions, e to the y squared over 2, are called Gaussians. And so we can see that this functional form, psi of y, would actually solve the Schrodinger equation. So it would be, since we have to take the double derivative of this function, it would be useful to do that right now. So let me just write down both the first and the second derivative of this function. And so the first derivative is, of course, the e you get back in e. So it's e to the minus y squared over 2. And now you have to take the derivative of the top. And clearly, that will give you just minus y. So this is the first derivative is that. Now you can do the second derivative, which is to take the derivative of that one again. So this is a product of two functions. So you use the product rule. The first one will give you e to the y squared over 2 times the derivative of minus y, which is just minus 1. And then the second term will give you the derivative of the exponential, which, as we have shown previously, is just minus y times, so the second term is e to the minus y squared over 2 times minus y, that's the derivative of the first factor, and then multiply by another minus y, which is the second factor. So that's just a square. Okay, so we see that this factor, this Gaussian factor, is present in both. So we can pull that out. And so whichever is left inside, as you can see, is just going to be minus 1 plus y squared. So because you will see this is a theme in these Gaussian functions, because of the Gaussian, the derivative of these functions will all have this Gaussian factor in front. So you see that's true for both the first and the second derivative. And in fact, if you keep on differentiating this, the third, fourth, and all the derivatives would also have the same form. They would be a Gaussian function multiplied by, in the parentheses, just a bunch of powers of y, a sum over different powers of y, right? So now that we know those, this is the second derivative, we put that back into the Schrodinger equation to verify that this in fact actually works. So you see the second derivative gives you this, and the second term in the Schrodinger equation has a y squared. It will give you essentially e to the minus y squared over 2 on the right. And that, as you can see, is clearly equal to epsilon times psi, where in this case you see that epsilon is equal to just 1. So, so I'll call that the first solution because we are supposed to have many eigenfunctions, and this is only the first one. I'll call that 0. And the eigenvalue corresponding to that, I'll call that epsilon 0. And so this is solution number 0. And in fact, in quantum mechanics, a lot of times we will use a different an integer to represent the discrete eigenfunctions, and that's called a quantum number. So in this case, I'll use quantum number n. So the number n, or the integer n, is the number that is essentially an index for these different eigenfunctions. And the first one I'll call n equals to 0, and that is psi 0 equals to e to the minus y squared over 2, with epsilon 0 equals to 1. So that pair of eigenfunction, eigenvalue is a solution to this problem. Okay, you might wonder why I do not start with n equals to 1, since this is the first solution, and you will see later on why. It just makes the counting a little easier. So now that you know what the first solution is, you can ask, well, can I easily guess what the other solutions are going to be like? I'll wait until a little later to show you how to do that, but you can guess at this point that the other eigenfunctions are going to be Gaussians of the same type. And if you take a Gaussian and multiply it by a polynomial, the derivatives of those Gaussian, first, second, third, and so forth, are all going to look like a Gaussian multiplied by another polynomial. So in general, these functions that are a Gaussian multiplied by a polynomial will solve the same eigenfunction, eigenvalue problem. So we will go back to this. We'll come back to this a little later on, but let me go back and show you something up above that I skipped over. So in this case, you see that the first eigenfunction is given by this purple curve right there. So this curve is psi of 0 of y, which is equal to e to the minus y squared over 2. And I've plotted two other functions. The first of them, this yellow one, is actually this term. So if you take psi and multiply that by y squared, you get this function right there. And the red one is actually the first term. So if you take d squared psi dy squared, you'll get the red function. And so as you add these two up, you can show that, well, that's actually negative. If you add these two up, you will get back the purple function, and that is one of the solutions of the Schrodinger equation. So I'm going to skip the rest of this page, go to the next one, so I can work through some of the math before I come back to this question of what are the other eigenfunctions. So let me just write that down before we get back to this question. So as we have said, we are going to assume that these eigenfunctions that we have are going to be some Gaussian function multiplied by some kind of a polynomial function of y. So I'm just going to write that as h of y. You see that in the first solution, this Gaussian is multiplied by just 1. In that case, h is equal to 1. So we expect to basically see a whole bunch of different eigenfunctions, and they're all different polynomials multiplied by the Gaussian. So what I mean by this is, since we know psi 0 is equal to this, then our conjecture for the other is going to be psi 1 is going to be some kind of function h1 of y times the same Gaussian, and psi 2 is going to be another polynomial of y multiplied by the same Gaussian. So you see the Gaussian factor in each of these does not change, but what is multiplied by this polynomial is changing. And so we can basically look at functions of this type and figure out what kind of h functions are required to make these, in fact, eigenfunctions of the Schrodinger equation. Okay, so if we do assume that this is the form of the correct form of the solution, then what we can do is to just take the Schrodinger equation and put in this functional form of psi that we guess is the correct form, and we can then discover what kind of h functions they must be in order to satisfy the Schrodinger equation. So let's do that. So again, to solve the Schrodinger's equation, we need the second derivative of psi. So let's do that. d psi dy. If you take this, again using the product rule, the first term will give me this multiplied by h prime. And then the second term will give me, as we have seen, derivative of the Gaussian is minus y times the Gaussian itself. So minus y h. So in fact, as we have seen previously, you can always factor out the Gaussian. So what is left inside is h prime minus yh itself. So that's the first derivative. For the Schrodinger equation, we need the second derivative. So we'll do one more. So the second derivative is another derivative of that. So again, this is a Gaussian multiplied by some polynomial. So using the product rule again, the first one will give me the Gaussian multiplied by the derivative of this. And then the second term will be the derivative of Gaussian multiplied by what's in the parentheses. Again, derivative of the Gaussian is y times the Gaussian. And this is multiplied by h prime yh. Again, factoring out the Gaussian factor as usual, we are left with these terms inside. You have a h prime minus yh. The prime is a derivative that applies to everything inside the parentheses. And you have yh prime minus minus, which is a plus y squared h. So that's that. And now we will have to do the derivative. So derivative of h prime is obviously h double prime. Derivative of yh is, again, according to the product rule, y times h prime plus derivative of y is just 1. So we have h and minus y h prime plus y squared h. And now you can group terms together. So let me finally just write that at the end. So this is going to be this Gaussian factor right here multiplied by, so I have 1 h double prime. I have this factor with a minus y in front of h double prime, another minus y, so minus 2y, sorry, h prime, 2y times h prime. Sorry, should not close the parentheses. And then finally you have this factor of h, and here is a y squared times h. So together you will get 1 plus, there's a minus sign in front, so you will get plus y squared minus 1 times h. And so that is just the second derivative of psi. Then the next term, the second term in the Schrodinger equation would be just y squared multiplied by psi. So together we have d squared psi dy squared. If psi is in this particular form, which will give me, which will give me that, plus y squared psi. And so what I will have is e to the minus y squared over 2 from the first factor, h double prime minus 2y h prime plus y squared minus 1 times h. The second factor will give me y squared times psi, which is e to the minus y squared over 2 times h. So now again, I can factor out this Gaussian factor. So at the end, this will give me the Gaussian. Now multiplied by, so let me figure out exactly how everything is going to work. I see I'm missing a minus sign in front of this. But instead of that, I'm going to just put that minus sign inside. So minus, plus, and then here I have a minus. I basically group all of these terms together. So I have a minus h double prime. I have a plus 2y h prime. And then you see that this minus y squared from this will cancel with a plus y squared, leaving me a minus times a minus 1, which is just plus 1 plus h. Okay, so that is what the left side of the Schrodinger equation is. The right side of the Schrodinger equation basically just says this should be equal to epsilon times psi. So let's put that in 2. So the right side of this equation should be equal to epsilon times psi, but psi is h times e to the minus y squared over 2. Okay, so let me change my colors so that this would be more obvious. So that is the Schrodinger equation, and so what this shows is what these h functions have to be in order to satisfy the Schrodinger equation. Okay, so to satisfy the Schrodinger equation, what you can basically see is that this factor is going to cancel out from both sides. They will never be 0. So whichever it is on the left, it is the same number on the right from the Gaussian factor, so that cancels. So what you can see is that whichever is inside this bracket on the left must be equal to what is on the right. So what that means is, if I make this conjecture for what the eigenfunctions have to be, that is, their Gaussians multiplied by some h function, then the h function must satisfy this new equation. So this new equation, so I'll write that down below. So the H functions must satisfy this new equation, and it is minus H double prime plus 2y H prime plus H must be equal to epsilon H. Okay, so if we want to find all the other eigenfunctions, then all we need to do is to find the H functions that satisfy this equation. So let's go back and first see that the first eigenfunction that we have already figured out in fact satisfies this equation, right? So again, the functional form that we are assuming is this. And in the first eigenfunction that we have found, psi is just equal to the Gaussian. And so what we see is for the first eigenfunction, H0, use another color, H0 is basically just equal to 1, right? Because H0 should go there. And let's see that H0 equals to 1 is actually a solution of this new equation in H. So let's do that, because when H is equal to 1, then the derivative of H is 0, double derivative is 0. So in fact, H is equal to epsilon H, where epsilon 0 is equal to 1, right? And so that is in fact what we have found. We have found that the first eigenfunction has an eigenvalue, epsilon 0 equals to 1. So the solution that we have found already for the first eigenfunction is in fact consistent with this equation. So let me just get rid of these numbers. So what that means is, in order to discover the other eigenfunctions, all I need to do is to find all the H functions that actually satisfies this equation. So let me write down the first one. H0 equals to 1 is a solution. So let's see if we can easily figure out what another solution is. Well, the next one to try is maybe H1 equals to y. That's fairly easy, because again, you can easily put those in, and then you can ask, well, what if H is y? Then H prime is 1 and H double prime is 0. So you can ask, would 2y plus y equals to some function multiplied by H, which is y? And so clearly the answer is yes, that does work, because what is on the left side is basically just 3y. So in this case, the eigenfunction, the eigenvalue that corresponds to H1 equals to y is just psi 1. But now you see that epsilon 1 is equal to 3. So this is equal to 3. So epsilon 0 is equal to 1. So you discover that, in fact, H1 equals to just y is also a solution of this equation, which then means that you have discovered the second solution for the Schrodinger equation, right? Let me now say one more thing, which is important. Now, you see, in this case, we have put in this, we have assumed that the first solution is given by this equation right there. Now notice that in order to for psi to be a proper wave function, the square of psi integrated over all x must be equal to 1. So there is some kind of a normalization constant right here, which I can call C0, which you need to multiply by the Gaussian by in order to really get this to be the proper solution. Now you see that the eigenfunction, eigenequation itself does not provide that C0 coefficient. And the reason is actually very simple. Again, going back to the Schrodinger equation right here. You see that there's a psi in every one of these factors. And so whichever coefficient the psi is multiplied by, so there's a C0, 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 and it doesn't really matter what that coefficient is, it will all cancel because they are the same in this equation. It will cancel from both sides. So what that means is that just finding the solutions of the Schrodinger equation itself will not pin down these normalization coefficients. In fact, this solution or this equation, the Schrodinger equation, or this equation for the H functions do not actually give you the proper normalization. It only gives you the proper functional form, right? So now going back using this solution, we can now go back and compare it to that solution. So we have found that the first solution, which we call n equals to 0, is given by this psi 0, where the h0 function is 1. So now this psi 0 function, or psi 1 function of y, we know is h1 multiplied by the Gaussian, and then h1 is just y. So this is the proper functional form. Again, there is a normalization C1, which we cannot figure out by solving the Schrodinger equation or this equation for H right there. So we are not going to be able to figure that out. But the functional form of the eigenfunction does not depend on what that normalization coefficient is. And then we discover that corresponding to that, so this is h1 equals to y, and corresponding to that h function, we see that epsilon 1 is equal to 3. So I can now call that the second solution, n equals to 1. So the n equals to 1 solution gives me the second wave function. Eigen energy corresponding to that, sorry, this is 3. The eigen energy corresponding to that is 3, and the eigenfunction is y times a Gaussian. So now that you've figured out the first two, you can see if you can figure out the next one. Since h0 is 1, h1 is y, it's not too difficult to imagine maybe the next one is going to be perhaps a y squared. So we can try that. So let's see if we can do h2 equals to y squared. And if we do that, then h would be y squared. The derivative of h is 2y times another 2y is 4y squared. And derivative of that again is 2, so there's a minus sign in front of that. Question is that equal to some epsilon multiplied by y squared? And the answer is clearly no. The reason is because of this extra minus 2, which is not on the right side. But then it's not too difficult to imagine, well, perhaps if I just add a constant to that y squared, it would have worked out. The reason is because instead of a y squared, if you have added a k, then this would come out to be y squared plus k. But then it would not have changed the h prime and h double prime because the constant k will differentiate out to be 0. So those two terms would have remained absolutely the same. But the right-hand side would have been y squared plus k. Right. So we in fact see that the first one would have worked with an epsilon equals to 5. The reason is very simple because you get a 4 there, a 1 there. And so the 5 multiplied by y squared would in fact be equal to the number of y squares on the left side. And now we fix this minus 2 because we can just make this come out to be equal to 5 times y squared plus k and find out what k is necessary to make that happen. So you see this 5 will cancel out those. So what I have is I have a minus 2 plus k. All the terms involving y squared are now the same on both sides, and so this is equal to 5k. So now I have minus 2 equals to 4k, so k is equal to minus 1/2. So now I know that my h2 is actually y squared minus 1/2. And corresponding to that, I've already seen that this eigenvalue, epsilon, is now equal to 5. So epsilon 2 is equal to 5. So that is the third solution right there. So I can go back and put that into my wave function by multiplying that by a Gaussian. So here are the two earlier solutions. And now I know that this third one is h2 equals to y squared minus 1/2. This is solution n equals to 2. So the corresponding eigenfunction psi square of y is equal to h2 e to the minus y squared divided by 2, and that is y squared minus 1/2 times this Gaussian. Again, the normalization is something that we cannot determine from solving the Schrodinger equation or the equation for h. We will have to fix that by the normalization of the wave function. But now we do know the eigenenergy. So the eigenenergy corresponding to this third eigenfunction is epsilon 2 equals to 5. So now I have everything for the first three. So you can essentially continue. You will see that the other h functions are going to be higher and higher powers of y. So you can also look at these eigenenergies, this one, that one, that one. And you can easily guess that, well, if the first one is 1, next one is 5, and so forth, these are going to be essentially just odd integers, 1, 3, 5, 7, and so forth, right? So these epsilons are going to be 1, 3, 5, 7, and so forth, with corresponding to these different eigenfunctions. Okay. And so you can easily represent that by essentially a formula 1 plus 2n, or 2n plus 1, where n is equal to 0, 1, 2, dot, 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 because these are odd integers. So that's why, as we have said, we've decided to call the first one psi 0, corresponding to that the quantum number is n equals to 0, because it's a little simpler to represent that based on these eigenenergies. Okay, but let's go back to look at what the actual eigenenergies of the harmonic oscillator is. So we go back to this Schrodinger equation, which we had rewritten using the scaling that we have discovered earlier. So that's this equation, and the corresponding epsilons are the true eigenenergy in units of h bar omega over 2. So now that we know what epsilon is, then we can easily see that in the harmonic oscillator, the true eigenenergies are the following. So the true eigenenergies in the harmonic oscillator are going to be En, which is going to be epsilon multiplied by h bar omega over 2. But epsilon is 2n plus 1. So these are the eigenenergies of the different wave functions for the harmonic oscillator. So you see that the harmonic oscillator energies they are different from each other by 1 unit of h bar omega, because 2n times h bar omega over 2 is equal to n times h bar omega. So every one of these is basically, the first one is 1/2 h bar omega, and then the second one is 3/2 h bar omega. So the difference is h bar omega. So oftentimes you would see this being drawn like this. If you have the potential energy for the harmonic oscillator, which is represented by this parabola, then the first eigenenergy is h bar omega over 2. The second eigenenergy is h bar omega over 2 times 3. And the third one is h bar omega over 2 times 5, and so forth. So 1, 3, 5. And then the spacing, or the energy difference between every one of these, is just h bar omega. So this unit, h bar omega, is called a quanta in the harmonic oscillator. It's basically the amount of energy that it takes to go up to the next eigenfunction. So let me just very quickly draw the shape of these eigenfunctions. So the first one, as we have seen, is just a Gaussian. So a Gaussian is fairly easy. So actually, let me draw the center line. So this is x equals to 0. And so the first wave function looks like that. And the second wave function, so this is psi 0. The second wave function, I'm going to draw on the other line. The second wave function is y times a Gaussian. We know y is an odd function. So when y is equal to 0, this psi 1 would have a node right there. On the right side of that node, the wave function is positive. On the left side of the node, the wave function is negative. So this wave function looks something like that. So this is psi 1. And finally, I have psi 2, which is y squared minus 1/2 times the Gaussian. So you see that y squared minus 1/2 would have to cross the 0 2 times. So there are 2 roots. And so as a result of that, this next function would have 2 nodes. You can actually work out where the nodes are. It's not that important, but there's one on the left side and one on the right side. And so the function will change sign twice. It starts on the far right with a positive, and then goes down, dip through below 0, and then comes back up again. So this function is psi 2. Okay. So before we leave this and go to the next part, I want to mention that if you think about what these wave functions actually look like and compare them to the one-dimensional particle in the box wave functions, you see that in the particle in the box wave functions, they also have no nodes in the ground state, in the lowest energy state, and then one node in the next higher eigenfunction, and then 2 nodes, and so forth. And that's the same in the harmonic oscillator. So these are related because the only difference between the harmonic oscillator and the particle in the box is, in the particle in the box problem, the particle is confined to a box inside which there's no potential. But for the harmonic oscillator, what is providing the confinement is actually the potential. So this potential right here, this potential 1/2 y squared, is essentially providing the confinement for the particle, but otherwise, when the particle is inside, its behavior is not unlike what you have seen in the particle in the box. So the wave functions are actually quite similar, except the confinement is provided by this potential. You also see that as you go to higher and higher wave functions, the wave functions are wider. The reason is because they have higher and higher eigenenergies, and that allows them to sort of push farther and farther out away from the center where the potential has higher and higher energy. This is not possible for the particle in the box because particle in the box has a hard wall, has a hard wall on both the left and the right. So the particle cannot push farther out when you go to higher eigenenergies. But for the harmonic oscillator, you see that the wave function actually becomes broader as you go to higher and higher eigenenergies. So that is essentially sort of the nature of all the wave functions in the harmonic oscillator and the eigenvalues associated with them. So you notice I've spent a lot of time going over these solutions because I think it's important to really understand what they are and where these eigenfunctions, eigenenergies come from, and because they do actually have an implication on quantum chemistry, and you will see this a little bit more when you go to the applications of quantum chemistry, such as in spectroscopy. So now we are going to go and finish the other two parts of the problem. These will be faster than the first part. So in part B, you need to prove these so-called recurrence relations of these H functions. The reason why they're called recurrence relations is, for example, if you look at the first one, you see that if you know the functional form of Hn minus 2 and the functional form of Hn minus 1, then you can actually figure out the next one. So if you know the last two, you can figure out the next one. In the second recurrence relation, it says if you know the functional form of n minus 1, then you can know the derivative of the next one. So these recurrence relations are actually related to the questions part C, which has to do with this the application of this position measurement operator x on the eigenfunctions of the harmonic oscillator. So let's take a look. So in order to prove those, we will have to first go back to this equation that tells us what the H functions are, and we need to modify that to make it a little easier. First of all, you notice that this contains this epsilon, which are the eigenenergies, but up above we have discovered that these eigenenergies in fact are essentially written as 1 plus 2n, where n is any of the integers, non-negative integers. And so what we can do is to just substitute that into this expression, this equation, since we know epsilon is basically just 2n plus 1. So now putting that in, we can move this to the left side. So on the left side, we'll have 1 minus epsilon, which is 1 minus 2n plus 1. And so when we have that, we will just be left with 2n. So this equation can be written like this: 2y h prime minus 2n times h, and that is all equal to 0. So now we have used the value for epsilon and transform our equation so that everything on the right side is just 0, and that's equal, so everything on the left side is equal to 0. Okay, so with that, I'm going to write down the two recurrence relations that I want to prove. So let's start with, in fact, the second one. I'm just going to call it Roman numeral 2. What that says is Hn prime as a function of y is equal to 2n multiplied by hn minus 1. So again, if I have the previous one, then I know the derivative of the next one. Now I need to, at this point, make a comment. So we have said that the normalization coefficients of all of these eigenfunctions, so which is right here, there, and there, we said that these we cannot figure out except by requiring the wave functions to be normalized. So whichever we have done up to this point, we are able to figure out the functional forms of the h functions and the functional forms of the eigenfunctions, but we don't actually know the proper normalization factor in front of each one. And you can see that very clearly in either one of these two equations, right? Because if you take h and multiply h by, if you take h, which is a solution to this equation, and you multiply h by any number, the equation will still be right. So solving this equation does not really allow you to actually figure out what the proper proportionality constant is. And so as a result of that, whichever relationship we are able to prove, we can't show the exact proportionality that is in this recurrence relation. So what we mean by that is, instead of proving this, the only thing we can actually prove is this is equal to something multiplied by hn minus 1. And now, to be completely explicit, let me write hn prime of y is equal to something times hn of y. So what this actually means is, for every value of y, this is true, but with the same constant. Since we do not know the proper normalization for hn minus 1, and we don't know what the proper normalization for hn, we know these only to some unknown coefficients. And since we don't know exactly what they are, we can't prove that this is exactly equal to 2n. But we can prove that the left side in its functional form is equal to the right side exactly in the same functional form, except we don't know how high these two are. So, and that is the reason why you notice I have called these functions that we have worked out, I've called them small h, and those are not exactly equal to the big H. So the big H, these are called Hermite polynomials. The small h are functional form wise, look exactly like every one of these Hermite polynomials, but I don't know exactly what is the correct normalization. Okay, so I think that's important to state. With that in mind, we can actually see quite easily how this actually works. But before I show this in general, what I'm going to do is to take the h functions that I know from the solutions above, and I am going to apply this recurrence to test to see if it's at least right. So we have two of these, right? So right here we have, let's say h1 is equal to y, and h2 is equal to y squared minus 1. So in this case, what I have is n is equal to 2. So hn equals to 2. So let me just write hn, because now I know n is equal to 2. So hn, as we have said, is y squared minus 1/2. And now hn minus 1 is y. So the question is the derivative of hn proportional to hn minus 1 for all values of y with the same proportionality constant? So clearly you can see that this is just 2y. So if I just then compare that against this equation I have, on the left side I have 2y. The question is that proportional to the left side, which is y? And I see in this case that in fact it is true. Except if, as I've said, if you put 2n in there, you see n doesn't really quite work out. But you see in terms of the proportionality of the functional form on the left side to the right side is true for every value of y with the same proportionality constant. So what I want to now, so I've shown you this actually works for 1n equals to 2, right? One special case, but it works for all case. And in order to do that, I have to prove this recurrence relation number 2. So again, I'm going to prove it for these small h functions. So the way to prove that is to basically take the take this equation right there, and we will differentiate both sides of that equation. Now, the derivative of 0 is 0, so that's nothing. So I need to differentiate the left side, and that will still be equal to 0. Okay, so what I want to do is to take the derivative of the left side minus h double prime plus 2y h prime minus 2n h. And that, of course, is equal to 0 still. So now I can do the derivative. But specifically, what I want to do is to apply this to hn. So let me write down hn, hn, hn. And now I want to take the derivative of hn double prime, and that is, of course, hn triple prime with a minus sign. The second term, I will have to use the product rule. So I would have 2y times hn double prime plus 2hn prime. And finally, the last one is just 2n multiplied by hn double prime, hn single prime. And that obviously is equal to 0. So now for this one, these two are both hn prime. So I can put these two together into one term. So this is 2 times 1 minus n times hn prime. And now I have 2y hn double prime. And this is minus hn triple prime. And that is equal to 0. So we know that is true because we started with the equation for h, right? So now you see that there's a hn single prime, hn double prime, hn triple prime. So if in fact hn prime is equal to something times hn minus 1, I can essentially just replace this by hn minus 1, and this would be multiplied by 2, let me reverse the sign there, so minus n minus 1. That would make it a little bit more obvious later. And this would then be hn minus 1 prime. And the hn triple prime would be a hn minus 1 double prime, if this in fact was true, right? And so the question is that true? And so you see that this equation right here is actually the same as that equation if you had used n equals to n minus 1, right? And so because there, all of these functions would be hn, hn prime, hn double prime. But if n was n minus 1, then you would have obtained this equation. So now we know, in fact, that that is, in fact, true. So we have proven this proportionality right there. And so now, if we know that that proportionality constant is, in fact, right, then we can actually just use this and make sure that these small h, whose functional form are the same as the big H, and make sure that they have this proportionality constant that is true for the normal Hermite polynomials with the properly normalized coefficients in front of them. And that relationship is 2n, or if you like, you can use that as a definition of what the derivative of the next n is when they relate to the last n, right? So what I can then do is to start with n equals to 0. I know that in my case, h0 is equal to 1. You can always start with the first one. And then and then we saw that in our case, we said h1 would then be equal to y. So you can ask yourself, what does that really satisfy the correct relationship reflected here? Well, the relationship, so we know that this h0 function is some proportionality constant multiplied by h0, and this h1 function is some proportionality constant multiplied by y. So if you apply this recurrence relation that we have just proven to those two definitions, then we can see if we can actually figure out what this correct proportionality constant is. So let's take this proper one and apply it to the big H Hermite polynomials, and then we will be able to figure that out. So h1 prime is obviously equal to this unknown constants y, and that we said is equal to 2 times n. But the question is, what is n? Well, you see the n that we are referring to is h1, so in this case n is equal to 1 multiplied by h0, which is 1 on the right side. Sorry, when I differentiate h1, the y should have gone out. So that is the relationship. So you see in this case, if I were to follow this particular recurrence relation, which is the proper one for the proper Hermite polynomials, big H, then the proper coefficient that I should use for the h1 function is actually not just y, but 2y. And so if we had chosen this recurrence to define our h functions instead of that one, which we know is true except for this unknown proportionality constant, then we can use them to actually define the proper Hermite polynomials, going from h0 equals to 1 and then to h1 to big H2 and so forth. And so you can then establish a correspondence between these small h functions that we have worked out and the proper Hermite polynomials, which are these big H functions. So now the next thing to do is to try to prove the second set of recurrence relations. So I'm going to write it here, and that says hn is equal to 2y hn minus 1 minus 2 times n minus 1 hn minus 2. And to do that, I'm going to make use of two things that I have already proven. One of them is this Roman numeral 2. So I'm just going to write that down here. So Roman numeral 2 we know is correct. hn prime is equal to 2n times hn minus 1. And the second equation that I know is right is this equation. Notice that this equation for the h function is true for both these small h functions as well as the big H functions too. The reason is because the small h and the big H functions are different from each other only by a proportionality constant. And this equation is insensitive to what the proportionality constant is, right? So let me write that down. So minus H, and now I'll use big H, Hn double prime plus 2y Hn prime minus 2n Hn is equal to 0. So these two are correct. So what I want to do is to prove that the combination of these two will in fact prove the first one. So using the first one, if we apply Hn prime to that, we get this. But if now n is equal to n minus 1, then I can rewrite this and say Hn minus 1 prime. But now n is n minus 1, so this is 2n minus 1, Hn minus 2, right? So using that first one, but applying it to n equals to n minus 1, I would have that relationship. But also, you see that if I take the derivative of the purple equation, this one, then I would also have Hn double prime equals to 2n Hn minus 1 prime. So I can derive these two equations, 1 and 2, from the pink equation. And now I'm going to put those back into the expression in the yellow equation. So putting these back in, we see that we have this one is given by that one, but that one contains an Hn minus 1 prime, which is given by that one. And back in this yellow equation, we have this Hn prime, but the Hn prime is given by that one. And we then can put all of these back in. So let me write everything back in. So again, Hn double prime is equal to 2n Hn minus 1 prime, which is equal to 2 times n minus 1 Hn minus 2. So whichever this is negative. I'm going to write everything out. 2n times 2 times n minus 1 times Hn minus 2. And then this one, Hn prime, is just equal to 2n times Hn minus 1. And clearly, this is just 2n times Hn. On the right side, this is all equal to 0. So you see that there's a factor of 2n that is in every one of these terms. And so you can divide out 2n because n is going to be an integer. And so when you do that, then you see that what is left is basically minus 2 times n minus 1 multiplied by Hn minus 2 plus this 2y multiplied by Hn minus 1 minus Hn is equal to 0. Okay, so that in essence is what we need to prove right here. So that is exactly that equation. So we have proven this second recurrence relationship, which I called Roman numeral 1. Okay, so these two relationships can be proven just like that. So finally, we can go to part C. Now, there's really nothing intrinsically very interesting about these recurrence relations, except it is quite interesting that if you know one, you can know the next one and the next one and so forth. But it turns out that the reason why this is important is because they have some implication on quantum mechanics in terms of its application to spectroscopy. You will learn later on that in spectroscopy, if you shine light on a vibrating molecule, a molecule that has a dipole moment. The light wave that is oscillating in the direction of the bond of the molecule is going to be able to excite the vibrational modes in this molecule. And the amplitude of the light wave in the direction of the bond is essentially an x. And so applying a light wave to a vibrating molecule or to a molecule that can vibrate is the same, is equivalent to essentially applying the x operator on the wave function. So it would be interesting to sort of figure out when you apply x to a certain eigenfunction of the harmonic oscillator, what does it do to that wave function? And that is provided by this recurrence relation. So to begin that, let me take this 1, this Roman numeral 1, and just rewrite that. So you see this is applied to n. So let's apply this to n equals to n plus 1. I mean, that doesn't sometimes cause a little bit of confusion. But what I mean is instead of writing n in this equation, you just put down n plus 1. Right? So applying this to the same equation, so you can see that this now can be rewritten as, again, just Roman numeral 1, but written for a different index. So in that case, you see that that comes out to be h of n plus 1 equals to 2y. Now, because n is n plus 1, if you put that into that equation, this becomes hn. And again, now n is n plus 1, so this is n plus 1 minus 1. So this is 2n, and this is multiplied by hn minus 1. So the same relationship you can write for a different index like that. Or what you can do is to basically regroup this equation and rewrite it like that. So you can see that I can rewrite this equation and say 2y hn is equal to hn plus 1 plus 2n hn minus 1. So multiplying y by a Hermite polynomial hn would flip it into hn plus 1 plus hn minus 1 with some coefficient in front, right? So that's what the recurrence relationship tells us. So now what we're interested in part C is to really understand what would happen to a wave function if I apply the x operator to a wave function psi n of x. Well, we remember the transformation that we made was y equals to x divided by L. So the x operator operated on a function psi is essentially equivalent to y operated on psi of y that we have just calculated. So we can see that the wave function psi of y are all going to be functions like hn of y multiplied by e to the minus y squared over 2. And so the question is, what does y do to that? And now you can see this from this relationship right there, because you see y multiplying by hn will generate hn plus 1 and hn minus 1. So what this gives you is, so if you put the 2, which is there, that makes it a little simpler. So you see this is 2y hn of y outside, and this is multiplied by e to the minus y squared over 2. Now, of course, what that does is to generate a sum of hn plus 1 plus 2n times hn minus 1, which is that. And of course, you see that this one is simply going to give me psi n plus 1, while this one will give me psi n minus 1. So what that means is that the operator y, when it is applied to a particular psi of n, will generate psi n plus 1 and psi n minus 1. So what that means is, as I've said, if you have a molecule that is represented by a bond like this, so you have A and then B, and if this molecule has some dipole moment, so let's assume that you have a minus charge on A and a plus partial charge on B, then when the molecule is radiated by light, which if the light field has a direction of oscillation that is parallel to the dipole moment of the molecule, then what this essentially does is to apply a operator x to the eigenfunction of the harmonic oscillator. And so what that does is the coupling of a light field into the vibration would actually generate, from starting from some wave function on level n, it would actually generate n plus 1 and n minus 1. So the light wave would actually either flip the current eigenfunction to a higher one or a lower one. So let me go back to like this picture that we had earlier. So for example, in this picture, we have the first three eigenfunctions of the harmonic oscillator. So what this means is, if you apply a light field to this particular bond, what would happen is you can take psi 0 and you can generate psi 1. There's really nothing below psi 0, so you cannot generate psi minus 1 because that just simply does not exist. But if you had started with a particle with the molecule in psi 1, then coupling a light field into that vibration would either generate psi 2, that is, change psi 1 and flip it into psi 2, and that corresponds to absorbing this photon and exciting it to the next level. But then it can also flip the psi 1 back into psi 0, and that's essentially an emission process. And so if you do that, you can then see that if you are on any of these wave functions higher up, coupling a light field into it can either flip it one eigenfunction up or one eigenfunction down. So that fact will actually become useful later on when we deal with spectroscopy. Okay, so here is the entire solution to the entire problem. Turns out to be a fairly long one because there are actually a lot of details. But if you understand this problem fully, you have understood most of what you need in order to fully understand the quantum mechanics of the harmonic oscillator.